Can you see something?
Okay, can you guys hear us now? Okay, great. Okay. Okay, so just to recap for those of you who are online, I am. Oh. Okay, are we good?
Yeah.
Okay, everything's good. Okay, to recap, for those of you who are online, I am Catherine Heller. I'm a researcher at Google Research. I lead the context and AI research team. We focus on having specific goals, and I will actually get more to our team in a second, specific goals for the research that we're trying to accomplish. And then I talked a little bit about our recent position paper at ICML, which advocates for finding a different North Star for AI research other than AGI, because people are very confused about what AGI actually means, and that leads to a lot of non-specific goals and misunderstanding about how to actually evaluate the very important things that we want to do. So we take an approach of specificity and also of human-centeredness, of trying to get the opinions of people who have had different experiences and learning from them and incorporating them into what we're doing. Okay, so our team is the CAIR team, and it's made up of the people you see on the right. Hopefully there's some familiar faces. Bonaventure, who is there at the bottom, just finished with us as a student researcher, focusing on wearable time series data and its ability to measure maternal health outcomes. And Nagar, who's in the middle, is an affiliate faculty member with you all and has worked on all of the creativity and imaging work that I'm going to be talking about later. We're a group of people who are dedicated to developing and evaluating AI systems that are grounded in real-world contexts and use cases, and focus on solutions that promote equitable outcomes. So outreach and inclusion are really central to what we do. And here I'll focus on applications to health and to imaging in particular. Okay, so I start with our health applications, and within causal modeling specifically, because it's fundamental in trying to formalize our questions and concerns and their solutions. We can design valid evaluation procedures, which are too often constructed in ineffective or harmful ways through the use of causal modeling. Causal modeling provides a way to formally incorporate important domain-specific information to ensure synergy between the predictive task that we're studying and trying to solve for and the actual deployment use case or context, and to move to deeply understand data biases, such as label bias or selection bias. Okay, so a key part of this work is understanding how to design machine learning systems that are appropriately grounded in the context in which they are intended to be used. This means clearly defining the intended use case and target population. So later we're going to see a classifier that identifies dermatological disease in images. We'd want to define how that model would be used in a clinical workflow, what the clinical setting is, and what populations it's intended to be used on. Ideally, we can use this sort of reasoning to develop contextualized statements about downstream impacts of our model. An issue that we need to address is that data used for model development and evaluation reflect very complex societal context, which results in differences in health outcomes, access, and quality. This introduces issues like selection bias, because data sets will be less representative of populations with worse access to care. And if utilization of healthcare is used as a proxy for the need for healthcare, as we've seen in many papers, this will result in the worst proxy for patients with poor access to healthcare. Okay, so here we'll focus on from issues that arise with basic evaluations of model performance across subgroups. We discussed cases where we're interested in evaluating performance across subgroups defined by an attribute like race or gender, but this can apply to any set of related contexts. Even in the best case, where we have representative data, comparisons of model performance across subgroups can be misleading because the optimal model performance tends to differ across different subgroups and can be explained by differences in the data distribution across those subgroups. And so we consider this to be a false positive fairness violation. What do I mean by that? I will get to that in 1 second, don't worry. But for now, we look at some of the most common classes of fairness criteria that include demographic parity and equalized odds. You see these a lot in papers. Demographic parity asks that model predictions be independent of group membership, and equalized odds asks that demographic parity or model predictions being independent of group membership hold conditioned on the outcome. So this is equivalent to requiring that the true positive and false positive error rates, and I'll get to this again in a second, not differ across groups. So there are variations of both of these criteria, both demographic parity and equalized odds, one for the continuous valued score S and one for the predictor Y hat. So this could be like your actual kidney functioning versus like your measured kidney functioning. Okay, we can see the commonly used evaluation interpretations that pop up in the research around us. Okay, so here's a simulated example. The top left plot introduces the notion of score distribution. That is the distribution of scores that a model assigns to a population or subgroup. So for example, kidney disease or eGFR is the number that's commonly associated with kidney functioning. For a given threshold, the classification rate is the fraction of patients whose scores exceed the threshold and thus would be assigned a positive prediction. So in the plot on the left, the threshold is given, or just in general, the threshold is given by the dashed line that's vertical, and the classification rate is given by the area under the curve to the right of the threshold. So that's highlighted in blue, or I guess in red on the y=0 piece. No, in blue, sorry. It's always in blue. Okay. So the classification rate is shown in the bottom left plot, right? So the threshold, the dashed line, separates the positives from the negatives, given the distribution for the class that's given by the blue line. And then the middle column and the right column are conditioned on having kidney disease, that's a y=1, or not having kidney disease, that's a y=0. And so the scores on the bottom two plots here, look at the really important one is the false positive rate and the true positive rate. And what we notice is that we take this threshold and we slide it from left to right. Here for the 0 class, the people who don't have kidney disease, the false positive rate goes to 0. And here for the people who do have kidney disease, the true positive rate goes to 0. Okay, that's our general setup, distribution, classification rate, threshold. Okay, so now we have two subgroups, right? So the blue subgroup and the brown subgroup, right? And we can compute these same things, both for the blue and brown subgroup. The threshold is, again, the dashed line. The fraction that we're classifying as 0 or 1 can be set by a classification rate, which is equal to the distribution under the curve to the right. And so what we notice is that there's like a gap. There's a gap between what we see for the blue subgroup and for the brown subgroup. And the gap is visible in the classification rate overall, and the false positive rate, and the true positive rate. And this gap really measures the difference between the distributions for those two subpopulations. And the point here really is that the optimal classification rate isn't going to be the same for those two groups as measured by the gap, right? And so we can see that it's going to be really hard to find one model with one set of parameters that is fair for both the blue group and the brown. Okay, so to better understand and model different kinds of shifts and differences that we see, we can use causal graphical models representing the kind of independence and conditional independence structure that we saw in the table a couple slides back, the table on demographic parity and equalized odds. Not only are we able to formalize the shifts given here, right? So this is like outcome shift, label shift, etc. But also things like selection bias, label bias, and other kinds of confounding. And we have created in various circumstances graphical models for all of these, and I will not sort of spend time on this here, but for further questions on sort of causal models and causal model inference and structure, you should contact Stephen Full on our team, who really spends all of his time doing this. I will point to one example that we did using dermatology. This was at NeurIPS a couple years back. And so if you look at the paper, there's the corresponding causal model structure is there. But this looks at what happens when we are trying to do a shift in terms of dermatology prediction from one hospital to another. So we might have sort of all kinds of out of distribution questions. What happens if we move from one hospital to another? What happens if we move from one demographic group to another? And this dermatological study in particular looked at trying to predict, I think it was 24 skin conditions across 2 different clinical environments. And so the one that was trained on was teledermatology in the US, and the target one that we were trying to predict out of distribution was in-clinic visits in Australia. And so this involved both a shift in demographics, but also images and labels. And basically on the right, what you see is the evaluation. And so these open dots are the dots from the training model, which you can see looks fair across groups, right? You're getting the same kind of predictions for all of them. But then when we shift to the black model, which is the target, which is on the target distribution, the black data set, which is on the target distribution, what you see is we do a good job on some groups of people, but not on others, right? So we retain good classification rates for young people, but really don't for older people. And this kind of demographic shift can happen across lots of data points if we're not careful about what we do. This is a really common thing. People take ML models, they train them and test them in a particular setting, and then kind of expect that the models that they develop reflect the causal structure that they think that they should. And so then they take them and they apply it to some other setting where they clearly should work properly, and they just don't, right? And they don't for all kinds of reasons, spurious correlations, all kinds of things. And this is captured here. And the causal modeling really gives us a framework in which we can formally think about all of these processes when it's possible, and to do sort of a rigorous study of what's going on. Okay, so recently we looked at evaluating large language model question answering around answers to health questions. So this work is on MedPOM2, which is one of Google's medically specific large language models. And you can see it here. The user can ask questions like, can incontinence be cured? And the model gives some kind of solutions, seen in blue, some kind of answer. So in order to understand fairness and equity challenges in a health context, we really had to do a couple of things. So first, we had to define a rubric. Like when I talk about fairness or equity, those are themselves vague terms, right? So nobody really knows exactly everybody's sort of got an intuition, but we haven't yet specified exactly what that means. And so aspects of fairness, aspects of equity were things that were decided on by a focus group sessions, focus group sessions with physicians. And they were done using sort of like the causal modeling context that I described, right? So we said, if our data looks a certain way and is set up to measure this kind of thing from a causal perspective, what is it that you as a clinician would expect to get out? And how is it that we would go about measuring that? So first we did the rubric definition, and then we collected a whole bunch of data sets. So this resulted in the Equity MedQA data sets that were gathered. So this is a collection of 7 data sets of adversarial questions containing a few thousand unique questions. And so the purpose of these data sets is to probe for potential bias within the questions, questions that somebody can ask that would plausibly lead to problematic outputs. So each of the individual data sets was created with some particular kind of situation in mind, right? So one was topically enriched for content related to health inequities in the US, and another one focuses on tropical and infectious diseases globally. This data set, which focuses on tropical, okay, so here are all of these data sets and more details about each of these data sets. To understand sort of details of the data sets, I'm going to refer you to the paper. This was a Nature Medicine paper last year. I'm going to talk more specifically about the tropical and infectious diseases data set, the TRIMS data set, because it's global and because we collected it and used it to prompt tune, to just do some simple prompt tuning of Gemini, which is Google's large language model du jour. Okay, so, I don't know how to do this. Okay, sorry, this is going to take twice as long as I wanted because I wanted to speed this up. It takes a while. All right, let me see if I can do that actually. Oh, there it is. There's my cursor. Okay, there's something going on. Wait. Oh. Okay. Let's see if it just takes me forever to do this. Okay. All right. Okay. Hopefully you'll have to wait a little less long. Okay, so this is a setting that's using the tropical and infectious diseases data set to prompt tune Gemini. We have a set of, somebody could use it, they enter their demographic information, they enter where they're living, they enter what risks they might have. So here, this person slept without a mosquito net. They can check off boxes for the current sets of symptoms that they're experiencing. They hit generate summary, they get a summary of the information that they put in, and then they get a large language model, what disease the large language model thinks that they might be experiencing. It gives a confidence measurement for that, or confidence interval around that, and then provides a map of the globe so that you can see prevalence of particular diseases in particular areas. And this is important because a lot of the things that come out of large language models are very US centric, and this is trying to spread things out so that we understand sort of like the context of where it is that you are, and what it is that you might have been exposed to from a disease perspective. Let's try that again. Okay, here we go. Okay, so okay, so that was one thing. That was the tropical and infectious disease data set. So that was kind of a cool just thing that we did in our spare time in order to show the value of collecting that kind of data and using that together with large language models, which is now there's a better understanding of sort of like contextualized like disease prevalence and what you might be exposed to different places. Okay, so also at the same time, or similarly, simultaneously, we worked on the largest study for large language models in African healthcare, and that was called AfriMedQA. And the way, okay, so this data set and project is really a collaboration between us at Google Research and a bunch of other organizations and institutions, particularly African African organizations like Sasanke Biotech and Masakani. And you can see them listed here. Okay, so AfroMed QA is a standard QA kind of data set, which focuses on the African context. So here it's presented, all of the Med QA data sets are presented as like you would see on a medical board exam, right, where you get like a contextual situation. So here a 2-year-old boy presents with a history of vomiting and diarrhea, and then you're asked as a clinician what you would do, and you're given sort of like multiple choice responses, and you've got to choose the best one. And we gave this to a bunch of people, but largely a bunch of African physicians, and we asked them to rate the responses that they were seeing coming out of the model. And the ratings were both based on quality, but then also of how much this is relevant to an African specific context. We took this data set, and we've used this data set a whole bunch of places now. Both of these data sets have been used in order to evaluate Gemini, but in particular, this data set, the AfroMed QA data set, was used as an evaluation for MedGemma, which is Google's current open source system for evaluating medically specific questions. And so you can see it if you look at MedGemma, which was launched recently. You can see it in the model card of what it does. I also wanted to talk about pregnancy intelligence and our work on wearables for the case of studying maternal health. And in particular, I wanted to talk about some of this work because this work was done in large part by Bonaventure, who's here at Mila, who you guys can talk to anytime. So if you have questions about it, you can ask him. Okay, so Fitbit, which is now part of Google, has one of the largest data sets on the use of wearables during pregnancy. So our aim was to use this data to make predictions about maternal health outcomes that might be useful for pregnant users down the line. And I will quickly go through this. Okay, so we have the pregnant users, they have wearable data coming in, and we want to say something that they find useful, right? That's our goal. And in particular, we were interested in predicting postpartum mood disorders from our multiple collected time series. And we were interested in doing this because mood disorders are incredibly common during and after pregnancy and are underdiagnosed and undertreated. Okay. So this is an example of the kind of time series data that we use to model mood disorders. You can see heart rate, you can see step count. Well, there's a distinct difference in the time series between women with and without mood disorders. So the women with the condition are represented with the yellow line, and without the condition are represented with the gray line. And hopefully you can see that if you just eyeball it, it's pretty easy to tell the difference between those two. And we tried a lot of different methodology for doing this prediction. And what we ended up with is a time GAN with a whole bunch of modifications, but most importantly, a latent space mapping, a non-stochastic latent space mapping, which helped us compensate for undersampling and helped us upsample the positive data. So you can imagine that there are many fewer women with mood disorders than without mood disorders. And so in order to obtain some sense of class balance, which was important in our situation, we needed to upsample the women with the mood disorders. And we used the time GAN with the latent space mapping in order to do that. And yeah, you can see here in the bottom curves that we were pretty successful at being able to predict anxiety, sadness, and depression. Okay, so for more information about this work has been accepted as a clinical abstract to the Machine Learning for Healthcare conference, and we're in the process of writing it up for journal submission. And if you have any questions on this, most of the work that I'm presenting here is actually relatively new, but like if you have any questions about this, definitely touch upon it, I'm sure. All right, so now I'm going to shift gears to talking about creativity in images. And so I'm going to start by talking about our work. This work was presented at CAIR this past CAIR. So the idea here is that image generating foundation models are very large models trained on very large data sets. And the data sets are heterogeneous. And we can say that all of the images and associated text on the internet fall under some joint distribution, P of X and C, which is just the ideal is sketched there. And different parts of the manifold of the data set could be used to represent different things and are potentially sampled at different frequencies, right? And so here we have a model, an image of a golden retriever. There we have an image of Picasso. So when we train text-to-image foundation models, we train them so that we can generate from a conditional distribution, P of X given C, where the conditioning represents different possible modes of the training data set or different classes. So for example, here, prompts related to retrievers might fall into this yellow category, prompts related to Picasso might fall into this deep green category, and they're potentially different. Okay, and the different conditions might be more or less well sampled or well fit. So for example, it could be that the golden retriever images are really well learned, but the Picasso images are not. So the performance of the text-to-image model is not uniform across the learned distribution. In traditional generative models, finding and understanding failure cases is easier. So we can look at the training distribution to understand if there's sampling biases or measure distances between training and generated distributions to understand how good the fit is. But doing this is intractable for the really large heterogeneous models that we're dealing with. And so we can ask, can we just use the pre-trained models parameters like weights and activations, which we're learning anyway, in order to act as a proxy for prediction? So in order to do this, we build a framework that probes the learned geometry of the manifold of the data condition on the class, right? We then study correlations between the geometric characteristics and the generation behavior in order to see sort of what comes out as we change the different properties of the manifold that we're learning. Okay, so a large class of generative models are continuous affine spline operators. This is an assumption that holds for a very large class of networks and for foundation models that have piecewise linear activation functions like ReLU, so it's piecewise linear all over. Continuous affine spline operators can be characterized in terms of two things. The first is the region-wise affine scaling, translation, or rotation. So region-wise scaling can be quantified in terms of ranking the rank of how many dimensions are retained after scaling, and what the aggregate scaling across non-degenerate dimensions. And then secondly, the spatial distribution of regions in the latent space. So the spatial distribution of like the number of regions, of piecewise regions, corresponds to the unsmoothness or the rugosity of the manifold. And so these are two characteristics which are going to be key in defining our metrics so that we can better understand this manifold of all potential generated images in our space. Okay, so the way in which we use this and we characterize the local geometry of the generative model is by local scaling, which is the local change of volume for a region, how much space it captures. The local rank, so the local dimensionality of the learned manifold, and local complexity, that's the number of regions inside a local neighborhood of radius R. And so then using those three different metrics, right? So this is just the activations and weights for the learned manifold that we get through pre-training. We look first to sort of validate that this is actually capturing useful information. So that we look at a latent diffusion model that's trained on the dataset Celoba HQ. And so that's a dataset of face images. And so what we see here, what this is a very complex way of showing, is that other face data sets are predicted well and are not sort of distinguishable from the original Celoba HQ data set, even with some amount of noise added, and that non-face data sets are very different. Okay, so generated stable diffusion images with higher local scaling are visually more complex, as you can see given here from left to right. So here we're increasing the local scaling left to right, and you can see very simple images to really complex images. Okay, and generated images with higher local rank from a higher dimensional part of the manifold contain more higher frequency textures. So these will be low frequency textures, and these would be high frequency textures. Hopefully you can see that the textures are very different. All right, so to confirm that the local geometry is sensitive to image aesthetics and visual complexity, we add interventions on the image that make aesthetic changes to the images by increasing or decreasing visual complexity. So we can see that that highlights two benefits from using local geometry. First, unlike distribution level metrics like the Venn score, so the Venn score is a metric for diversity. So if you have a set of images, how diverse are they? Local scaling is an example level property, and so it doesn't take a whole distribution of things, which makes it ideal for things like reward modeling. Secondly, this means that there isn't a need for an external reference data set. And so we look to see if we can control different aspects of the images that we generate using the properties of like the geometry of the manifold. And so here we're looking at controlling for generation diversity using local scaling as a reward. And so you can see that we can kind of play around with certainly like how sensitive we are to how noisy the background is in the models and things like that. So we can try to pair up images with different levels of that going on. And here also, hopefully you can see that, and this is maybe nicer left to right, you can see that increasing the local scaling to higher visual complexity, right? So again, that's well controlled, and we can try to mix that around. Okay, so in summary, we can use the geometry of the manifold to audit foundation models in a way that garners more trust. So a trustworthy audit means that we have to be able to understand causal effects of the system, design choices, and the ramifications for society, right? So the more control that we have, the more trusting people are going to be of the system. And so this is just a first step in that direction, right? Like looking at specific metrics, looking at how well they fall under our control, what they might mean, and how that might affect sort of like things like the diversity or simplicity of the images that we can generate. Another property that we'd like to, oh yes.
How do you calculate this local dimensionality weighted number of non-zero values? And secondly, don't you say these like prioritization of algebra or something like that. And the reason I like saying this is because like this way of like counting the number of small like regions and stuff. There are a lot of like small regions because they have all of these results, the other rank distortion, like angle distortion, all of these things that there is no way that we can find those small regions because of like the floating point error and this stuff. So and like a lot of information about our world model or like these diversity things that you're looking for may be included on those small regions.
Yeah, I agree that there are lots of different choices in order to try to get at some of these properties, right? And you might be able to find better ones. I hope that we can improve off of this, right? Like this is really just sort of like a first stab at trying to move in that direction. For the details of what's going on in terms of exactly how things are being computed, definitely look at the paper and talk to both the GAR, who's here as an affiliate faculty member, and also Imtiaz, who was the first author of the paper, and they'll be able to get more into the specifics of the actual counting. But yeah, no, I definitely agree that there are more and better ways to potentially go about doing all of this, and it would be great to see. But just having a first step towards controllability of some of these properties that hadn't been done before in the literature, right? And so it's just an attempt to say, okay, we should be moving in this direction. So another property that we'd like to be able to control in the images that we generate is the presence or absence of particular concepts. Generated images are very good at capturing a wide range of styles and concepts and are trained on large data sets, allowing for the revealing of private or sensitive data. So being able to include a particular concept in an image generation is a sought after, or not include a particular concept in image generation is a sought after goal. Okay, so a line of concept erasure techniques that have come out in order to try and achieve this goal. Okay, so we look at a line of concept erasure techniques that have come out in order to try and achieve this goal more efficiently than needing to retrain. Because so one can always retrain the model without the training data of the thing that you want to get rid of in it, but that's like really, really time consuming. And we want to be able to find more ways that we can potentially get rid of that. I think personally, I'm a little skeptical about how good we are at doing this, how quickly, but we're trying to do it because it's just so time consuming. And it's such a big issue for us, both from a safety and other kinds of perspectives. Okay, so there are many motivations, privacy, safety, but being able to do this well remains elusive. Okay, so we developed a framework for the evaluation of concept erasure methods, which are characterized by the features which are listed on this slide, which include accuracy, sensitivity, robustness, and diversity. And you can see those in a whole bunch of cases. And so we tested the concept erasure methods that are commonly used in 3 different situations. And so those are really what I'm going to focus on here is those 3 situations and the fact that we should be looking more at these situations because they're boundary situations that might be able to distinguish important properties of the models in a context, or in a concept erasure sort of like in a concept erasure kind of space. Okay, so the first is concept interdependence. So this is when multiple nearby concepts have shared characteristics. So here we're looking at can the method erase one of those concepts while leaving the others intact? So we're interested in, say, being able to erase a concept like kitten, but keep a concept like puppy. Those 2 things, a kitten and a puppy, they share many, many aspects, right? But we'd like to be able to separate them out. Okay, and here we show an example of erasing a cat and prompting with a tiger. And really what we want to point out here is that you can erase the cat, but once you do that, you're seeing a lot of distortion of the concept of tiger, right? So you get the really elongated bodies, and those just aren't being generated that well. So that's the kind of problem. And in the paper, so this is an ICCV paper that's about to come out at ICCV, and you can look at it for more details. There are all kinds of like actual quantitative evaluations. I'm just kind of quickly going through some of like here you can see an example of this problem. Okay, so this is an example of a problem with tiger generation. And again, for more quantitative results, look at the paper. Another situation is partial erasure. This is when somebody wants to get rid of part, but not all of some category. So here we show the erasure of black cat. So we want to erase the cat, but only when it has black fur and not in other situations. And here's a result showing that black cats are erased. So black cat on the stairs, don't see black cat on the stairs. But then so are orange cats and tabby cats. So anytime we ask for cats of any kind, they're not there, right? And so this is another common problem that pops up in a lot of these very common concept erasure methods. And then the last situation is when two concepts co-occur. So like peanut butter and jelly, you often find them together. So here in this example, we're erasing the concept. We're erasing Walt Disney. And so basically the point here is that not only do we erase the real Walt Disney, right, but we also erase Minnie Mouse, we also erase Cinderella, right? And so what it is that we're getting after and how the concept erasure techniques are working and what the results are going to be is something that really we need to study more. And so in particular, the works discovered a bunch of safety concerns around conflation of animals and humans. Maybe this comes up more working in tech, but like the conflation of animals and humans is actually a quite significant safety violation, right? And so here you can see the erasure of cat, and the prop beside me is cat, and there are people, I don't know, maybe because of the name cat, people sometimes copy cat, I don't know. So maybe that's like a thing. People come up, or that here you erase cat and then prompt for like a tiger or a lion, and you get people in tiger or lion suits. Okay, so the kinds of things that our evaluations have uncovered have been basically, the point is they've been underexplored in the concept erasure literature. And so careful assessment of these concepts, interdependence, binomial relationships, and partial erasure are going to be helpful for evaluating concept erasure techniques going forward. Okay, so again, for more information, more details, more quantitative evaluations, see the ICCV paper, and reach out for all of the imaging work, reach out to Nagar Rustamzadeh and Mohammed Halai, who are here in Montreal, or I think Ibtihal Amara, I saw her on the call. Definitely, she's the first author of all of this work. Reach out to her. Okay, thanks.
It's on YouTube, so you can just like ask a question and the presenter could repeat the question for the people.
Yeah, sure, no problem.
She's using her microphone or computer anyway.
Maybe you can repeat the question.
Sure.
Only like just a quick clarification. So you do this concept erasure during training or during things like I just want to clarify each part of the all the sort of thing this. Are you doing training or
No, post training. Yeah. So I mean, I think sorry. So the question was, like when are you doing the concept erasure, and whether it was being done during training or at some other point. And so the idea behind these concept erasure methods is that you can take a trained model and then go back and erase concepts from them without having to do things like worry about the training of the data set or retraining it, because that's very, very complex.
I guess I was wondering, there's a lot of connections between concepts that you're showing as well. Are there cases where it's not such a bad thing?
Yeah, I mean, definitely. Okay, so I am not the expert here, right? I will start by saying that. But I definitely, when I look at those examples, I have the same question, which is like, at what point do you mean to like delete all of Disney when you say Walt Disney or whatever, right? And so that's something that issue exists, right? Where you can say one thing and sort of like more broadly erase a general goal. But it's a problem with the English language or with language in general, right? Is it's not always clear in what context you're referring to a concept that's how specific, right? And so really, I think what I'm advocating for is having a good understanding of when you see this kind of thing happening, and understanding that's what you're going to get out of the method, and then being able to control for it in a way that makes sense for your particular application.
I guess kind of related to the other question. Then how, like the models are trained with all this, and then you're removing the concepts. You have to be like careful about how long you train that concept out. It's early stopping, and then touchy part of thinking, like how long do you go before like, oh, I went too far and now my fingers are getting a little longer. Is there some place where you can evaluate that beforehand?
Yeah, I mean, I think all this depends on the method, right? Like we had looked at a very, very large number of methods, and exactly which method does what in terms of like how long you let it run will really depend. And exactly what was done for this paper, I don't know if Ibtal is online, she might be able to also answer.
Oh, hi, yes.
She was the one who implemented all this. Oh, Ibtal,
Yes,
you were
hi.
trying to say something.
Yes, what was the
Is there a
question?
way that you can let her speak? Oh. Volume's up.
Yeah, can you hear me?
Still trying to say something. Interestingly, the microphone and the speaker were selected separately. So right now, because I went to the microphone on the laptop, the speaker is not actually still the one on the laptop.
Yeah, when I'm asking to type on the chat, I think there is an issue with the root today. They said like with the sound settings.
Yeah, definitely. Because Ibtal is definitely trying to answer your question in more detail, and she's the one who's really capable of doing it because she ran all of these experiments. Yeah. Oh man, I'm having a problem hearing you. I'm so sorry.
Joint distribution of the daytime concept to train?
Oh no. So okay. So I'm sorry if I'm misunderstanding you, but I mean the image generation technique is just trained off of like all of the image data on the internet that the company finds who's doing the training. I mean here, so certainly in the original one we were using Stable Diffusion, right? Like, so it's like whatever Stable Diffusion finds, Stability AI finds acceptable to train off of, right? And I think they don't care about concept erasure in particular, right? They care about image generation and generally image generation quality, right? And so they'll do a lot of tuning their data for image generation quality that they measure in various ways, but not for concept erasure in particular. Those are post hoc methods that come into play sort of like after all of that is done in the image generation technique or something.
So I think someone asked a question online. So they're saying, I have a comment regarding the health part. So it would be interesting to hear your views on how it relates to it. The fundamental issue is with the approach of health groups that is incredibly reductionist. However, modern medicine has worked extremely hard to move away from reductionist models towards a more holistic, people-centered approach. So this work in engineering seems to be taking a step back towards something that doesn't work all that way. I don't know.
Wait, I'm having a hard time understanding.
Yeah, even I'm having a hard time understanding. So I think the comment is more about I actually don't
Sorry,
know.
may I explain?
The fundamental issue of the approach is speeding the reduction is. I don't know if I can just can you clarify?
Okay, so I'm not exactly sure what exactly is being gone after here. They're saying I can explain more if I can speak. I feel like for future talks, having the ability to have people online speak is probably a good thing. So there are a couple of things that I can say. So one, again, is to refer you to the person who has most closely done this work, who is Stephen Full on my team. The other is talking about a reductionist technique. And I guess the thing that comes to my mind is sort of like the causal framework and causal modeling, and being able to lay out specific causal interactions is something that sort of limits in some way our ability to do that. And I kind of see that. So I was trained as a Bayesian, right? Like in a way I see this as a bit analogous to that, right? Like when you can do it, it is the thing to do. And when you can't do it because things are too complex, it's a good thing to think back on as an ideal, right? And to understand sort of the approximations that you're making from a causal perspective in order to be able to do the kinds of causal inference you're trying to do, right? And so it's easy for me to believe that there are models which are not as reductionist in that way, and I'm not sure if that's what the person is getting after, but that is definitely the best answer I can give at the moment.
I can just think of one hack to make people speak on. Let's just switch back to your speaker, right?
Yeah.
Oh yeah, that works.
Okay, so we can repeat the question now, hopefully. I'm super sorry. I mean, I guess while we're on here, Ibtihal, is there anything that I missed that you were really, really keen on saying? Because I feel like you should get the opportunity to speak if you're there.
No, you've done a great job, Catherine. Just like if you have any questions, please ping me in here. I'll try to answer everybody's questions. And the new version of the paper is going out soon in a week, so the camera already is done. And hopefully, please like go through that. And it's a data set that we're also releasing. So if you would like to test, if some of you are working on concept erasure, I would please like go test and use our data set. And yeah. But thank you. Yeah.
Thanks so much, Ibtihal.
Thank you. Great job. Thank you.
Okay, so I feel like everybody who has wanted to has gotten to speak. And if you have more questions, I'm here. I'm actually here all of next week before I go back to, I normally live in San Francisco, but definitely reach out anytime. I'm around.
Speaker.